this one is S equal to minus 4 plus J4 and complex conjugate. Okay. So we have this. And again, we determine the portions on the real axis, which is this portion here. Okay, so in this way we expect, because that is the direction of increasing the value of k, meaning 2 branches. So the 2 branches will meet somewhere and then break away. Okay, so we simply make a mark there and identify these things. And now for this one, also starting from here, so we can say that is we have, say, certain departure angles we need to find out. So basically here, let me just simply draw it in this way. So that is departure angles here. Okay, we need to also find the departure angles. Okay, so I'm going to label the information we need. And also here, 4 branches. So 2 branches will split away and then going somewhere, to the other 2 branches will go somewhere. So at this moment, it would be wise for us to find the asymptotes first to approximate their eventual behavior. Okay, so here we'll do the asymptotes. The orientations. If you remember, let me plug in equations directly. So that is the here we have the m degree of the numerator equal to 0, degree of the denominator equal to 4. Okay. If you remember that formula, that is n minus m and 180 degrees plus L times 360. Okay. So for this case, this is 4, right? So from here, we should be able to determine this angle by keep changing the L integers as an integer. So that is 45 and 135 and 225 and 315. Basically, 45 is something like this. Okay. And then 135 is something like this. Okay. And then basically something like this. Okay, so here we know basically it's kind of the asymptotes. We have 4 asymptotes. The asymptote basically forming a big X. Okay, on this one. So now we determine the next one is we determine the intersections. Intersection basically is, again, the formula is n minus n. I forgot that one because I tried to catch up the time. So otherwise I can redo from the beginning. So that is the n minus n, the summations of the poles minus the summation of the zeros. Okay, so that is 4, and summation of the poles is 0, and minus 4, and minus 4 plus J4, minus 4 minus J4. Okay, so that is this one, and we don't have the zeros here. Okay, so that is minus 3. So intersecting is here. So that is, so this is here. So here I can draw this in the good way. So this is the intersection of the asymptotes and forming into the big X. Something like this. Okay, good. And the breakaway point, I want to determine this is the breakaway point. The breakaway point is determined by this. We simply dk ds equal to 0. And what is k? K by this expression, you can see basically k equal to s plus 4 times s plus the interior is s squared plus 2ab a squared s plus 32 right now I expanded the last term into this. So basically that is s plus 4 and s squared plus as plus 32 equal to 0. Okay. So basically you simply implement this one. That one, basically this one is ds and s4 plus 12 s3 plus 64 plus 188. Okay, so then you simply take the derivative on this one, then you should be able to find the s will be equal to minus 1.577 in addition to the other two. The other two I don't have, but the other two apparently won't fit into this range. So we'll pick out this one. So this one at the breakout point is as equal to minus 1.577. So now we can find the branches. So the one branch is go here, one branch go here. And there's an asymptote nearby. We simply follow up and eventually go to 45 degrees. Okay, the other one is symmetric, reflective symmetric. Okay. So now for this case, we want to determine what is the K start and what is this value, say omega equal to how much, right? The intersections with the major axis. So for this case, we can apply either way. So for these characteristic equations, we can rewrite it into this as 4 plus 128, 12, s3 plus 64 s squared plus 128 s plus k equal to 0. Okay, let me rewrite this one. Simply is I multiply the denominator to every single term here, then rewrite into this. So we know that at this point is a j omega. We know intersection is a pure imaginary numbers. So simply introduce s equal to j omega into this equation. We solve for omega and k simultaneously for these numbers, for these conditions. So that means j omega okay, so from here we have two values, and I leave that detail to you. And here we can solve for omega equal to 3.266 and k value equal to 568.89. So that means k star here is 568.89. And this omega here is j times 3.266. You good? Okay. And now we resolve the two branches, and then we take care of the other two branches. Okay, so for this branch, then we can determine the departure angles. Again, we use the phase angle criteria, so that is the 1 and s plus 4 and s plus 4 squared equal to minus k angle equal to 180 degrees plus 360 degree times L. Okay, good. So basically this is the phase angle of 1 and minus the phase angle of s plus phase angle of right. So here we simply apply the phase angle criteria to the original characteristic equations. Okay, okay? Okay. So from this one, we can, based upon our drawing here, so this is our small test point. The test point very close to that point there. So now for this one, basically this number is 0. Let me use this column. So this is 0 degrees. Okay. And this one basically representing is this point to here. Okay, so allow me not to draw it, but from here, this point is very close to that one in respect to this. So this one should be equal to 135 degrees, right? We'll look at from the graph. You good? Basically, this point is very close to this. So we measure from here to here, that angle is 90 degrees plus another 45, 135. You good? Okay, and how about for this one? To 4, so that is that point to this one basically is 90 degrees. If you have any questions, stop me now, because I don't do the calculation, simply observe from the graph. Okay? Everyone with me, right? Okay. And now, this one representing is the phase angle to the two complex conjugate poles. To this pole here, locally, basically that is one of our departure angle we want to look for. And to another complex conjugate poles here, that is basically is 90 degrees. Okay? Okay, this one is minus 180 plus L 360. So solving this, then you should be able to get it is minus so that is minus 335 or 2 to 5 degrees. Okay, either way. So now we can draw it. So this is a horizontal line here. So minus 135, so that should be in this rotation. So that one is minus 335 degrees. Okay, so locally is departure in that sliding directions, and we see there's a nearby asymptotes. So basically this one will converge to this. Complex conjugate, this one will be something like this. So this one again, this is 135 degrees, and then going down, and then going up, and then going down like this. Okay? When I do the grading, I want to look into the details of key features. Like locally, the departure angle will be correct, the intersections of the asymptotes will be correct, and of course the correct labeling of the poles, and then this point intersections to the lateral axis. And those are the key points I'm looking into from your exercise. Okay, so time is up.